All right, so in the previous lecture, we were able to explain why we saw different lines on the line spectrum of a hydrogen discharge tube. So we used the Bohr model to explain that those lines come from the transitions of electrons falling from higher energy levels to lower energy levels. And when that electron falls, light is emitted during that energy transition. And so we were able to use the Bohr model to explain this and calculate those wavelengths and energies numerically based upon integer value energy levels. So we know electrons lie in these orbits or energy levels around the nucleus of an atom. So now let's get into the details of, what exactly are these energy levels and some more details about them and the electrons, and thus we will learn more about the electron structure of atoms. So that brings us to the de Broglie hypothesis. So what this hypothesis says is it just draws a comparison between the light duality that we've talked about, that light can both be a wave and a particle. Right, so light as a wave, electromagnetic radiation, and light as a particle, a photon, that we use to describe these energy transitions of electrons emits a photon or a packet of light energy. So the de Broglie hypothesis just draws comparisons to that. If light can be both a particle and a wave, then electrons can also be a particle and a wave. So Louis de Broglie, he kind of just made this wild speculation saying, okay, if light can do it, so can electrons. But he didn't have any real data to back it up. But eventually other scientists came in and was able to verify his claim that also electrons can be both a particle and a wave. And in the end, he won a Nobel Prize for it. But with the help of some other people. So, we've already proposed this equation for photons, relating the energy of a photon to its wavelength or its frequency. So for photons, this equation, E equals Planck's constant times frequency, is describing it as a wave, light as a wave. But we can also use Einstein's equation, E equals mc squared, and show that a wave can also have mass to it. So we can take the energy that we calculate from a photon with a specific wavelength and set that equal to Einstein's equation, E equals mc squared, and get that the energy associated with that wavelength or with that frequency is equal to the mass, the effective mass of that photon of light times the speed of light squared. So speed of light is a constant, so we know that value. And so we can calculate for mass. We can determine the effective mass of a photon of light. And so what this next line has, we just set equal this part of the equation of our photon, our wave light equation, and then we set it equal to Einstein's equation that relates mass, effective mass of a photon. And then if we just kind of cancel out the extra c's that we have, we can calculate that the wavelength of a photon of light is equal to Planck's constant over mass times the speed of light. And so you see here we can relate the wave components or the wave properties of some light to its effective mass of that light. So we can relate both the wave and particle nature of light in one equation. And that's what this equation says. The equation gives the wavelength of a photon traveling at the speed of light in which it has a effective mass associated with it. And so what de Broglie says, using this equation, he says, okay, if light with a certain wavelength can have an effective mass, because remember, h, Planck's constant, and speed of light are constants. So if the wavelength of light changes, so does the effective mass. So what de Broglie says is that if light is both a wave and a particle, can have mass, then all objects can have both a wavelength and a mass. So that's essentially what he said. If we can apply it to light, we can also apply it to materials. And that's essentially what this equation is the de Broglie wavelength. So essentially these two equations are the same. So if you have an object moving at some velocity, so we just changed c, the speed of light, to velocity based upon a material that is moving. at a certain speed or certain velocity, we can get that the wavelength of that material that's moving through space at a certain velocity is related to its effective mass. And this is how, in this equation, we can essentially say that electrons can have dual properties. It can both behave as electromagnetic radiation because of the wavelength component, and it has particle properties because of its mass component in this equation. All right, so we went from talking about light duality, so this is specific to light, or electromagnetic radiation, and then this equation, which is essentially the same, is just applied to actual materials that are moving through space. All right. Okay, so some notes here to think about. So if we think about the constants here, well, I guess there's only one constant, h. H is Planck's constant, and it's very, very, very small. If we look at that, the number for that constant, it's 6.63 times 10 to the negative 34 joule second. So the wavelength that you calculate from the de Broglie wavelength calculation, the wavelength will be really, really small to detect unless the mass of the particle is very, very small. And so this is how electrons get put into play, because the mass of electrons are very, very, very small. The mass of an electron is 9.11 times 10 to the negative 32. So if we put that mass number in the denominator and we put Planck's constant up top, we can see that when we multiply those things together or divide them, that we can get out a wavelength that we can actually measure using instruments. And again, so de Broglie came up with this, but he had no evidence of it at the time. But eventually, more scientists came in. Einstein supported his idea, and eventually he was given a Nobel Prize once all of the observations and experiments were done with his hypothesis. So yeah, eventually he got that Nobel Prize. So this equation, de Broglie's wavelength, laid the foundation for electron microscopy. So it's just a different type of microscope. So if you think about the microscope that you use in like biology class or something, you have your lens and you're looking at your small object. In a regular biology microscope, incoming light is hitting your object, reflecting and absorbing some of the white light, and then the light goes into your eyes so you can see and resolve the image that you're trying to look at. So a regular microscope uses light, visible light that has a certain wavelength, right? To resolve those images. What electron microscopy does is it doesn't use white light, visible light, to resolve images that you're trying to look at. Instead, it uses electrons to reflect off surfaces, and it's not going into your eyes. Instead, it's going to a detector that can detect electrons and resolve even smaller images. So when you see images of atoms, molecules, really, really small nanoparticles, all of those are done with electron microscopy. So instead of using white light, or like a regular microscope for biology, to resolve those images, it needs to use electrons to reflect off of those surfaces and those items to resolve really, really small particles, such as nanoparticles or even atoms. Okay, so what does that all have to do with electronic structure? Well, de Broglie kind of paved the way for us to understand electrons a little bit more. He proposed that electrons both are a particle and a wave, just like we talked about light. And so this brings us to looking at the consequences of this duality, this dual nature of electrons. And this brings us to the Heisenberg uncertainty principle and quantum mechanics. So all of these scientists, chemists, physicists are trying to figure out, what are electrons doing around the atom? All right, so we know that electrons are moving really, really fast. They're zipping around the nucleus of an atom. So what the Heisenberg uncertainty principle says is that the more precisely we know the position of an electron, because remember, it's zipping around the nucleus. So the more precisely we know the exact location of an electron, the less precisely we know how fast it's going at that instant. So an example is like, okay, if we're talking about like NASCAR race cars, and right, they're zipping around, the racetrack. All right. So if NASCAR's going on and we take a snapshot of the racetrack, right? And then we look at that picture. In that picture, you see all of the race cars just stationary in the picture, because you've essentially taken a measurement or snapshot picture of those race cars in a certain position at a certain place in time, right? Because you just took one picture. So that just gives you one picture, one snapshot in time of where those race cars are around the track. But when you take that picture and you know exactly where their position is, what we lose is information about how fast they're going, because you just took a snapshot and now in that picture they're all just stationary. So we know nothing about how fast they were going. In order to understand how fast they're going, we have to, take a step back and watch them keep going around and around the racetrack in order to measure how fast they're going. But then if we do that, we don't know what their exact position is at that time. So this is essentially what the Heisenberg uncertainty principle says, that but instead of race cars, it's electrons. So for electrons, the more precisely we know, we measure where they are, the less we know about how fast they're going. And so it's this essentially like balance between position and momentum or speed. So just remember, momentum is like velocity or speed, that we can't know both with 100% certainty at the same time. So we either have to know, kind of know what its position is, and we kind of know how fast it's going. And so it's this balancing act that we can't know one for certain without losing accuracy in the other. So what's better, instead of knowing one for complete certainty, is to kind of have a probability. Instead, if I say, okay, I kind of know where the position is, I can say, okay, the electron is somewhere in this space, then I can know a little bit more about its momentum. And so that's where these probability maps come into play. So you might know about electron orbitals. Those orbitals are just probability maps of finding where that electron may be in space. So if you think of like, s orbitals, p orbitals, that we'll talk about later, this is probability of finding an electron in that space. And it all comes to the Heisenberg uncertainty principle and quantum mechanics. So we can use quantum mechanics to solve for the probability of finding an electron in a certain space. This is how we get the different shapes of the orbitals. And so Erwin Schrödinger was the one to really coin the wave equation that you see here using quantum mechanics, which is just a different type of math approach. And so it looks really simple, right? So so this is this like pitchfork looking thing is called psi, which is a wave function. So that pitchfork, it's wave function. It's just all the properties of an electron within this wave function. So it looks really simple, but it's not. It's a new, more robust type of math. But really what you want to get out of here is that Schrödinger was able to solve for the hydrogen atom using this wave function. Essentially, he found that the energy of a wave of the electron in a certain orbital is equal to a Hamiltonian operator times that same wave function. But out of this, so this new little sign psi, our wave function, in terms of electrons and thinking about solving for probability of finding an electron, we can determine their location using psi, or our wave function, from the Schrödinger wave equation. So if we take our wave function and square it, we can determine the probability of finding an electron in a certain location. And that's what brings us to quantum numbers. So from the wave equation and the Schrödinger equation, that's what this is, the Schrödinger equation, we can determine quantum numbers. And that is what we will be studying here, the different quantum numbers to describe the location and properties of an electron. So we're not going to actually go into quantum mechanics. We'll just look at what numbers we can get out of quantum mechanics through quantum numbers. All right, so before we get into quantum numbers, I just want to announce that we are pretty much done with math stuff until we get to chapter 9, which is on gases. So the last bit of math that you'll see for a while is the de Broglie wavelength and our Rydberg equations. So that might excite some of you. But instead, with these next sections and topics, we will be applying concepts to different systems. So let's look at quantum numbers. So these numbers, these quantum numbers, are essentially associated with the solution of the wave function that came from the Schrödinger wave equation. So remember, the wave function is psi, the little pitchfork looking thing. So if you solve for the wave function for a hydrogen atom using the wave equation and get the exact solution of psi, out of there, you get these quantum numbers. And so that's what we are looking at. We're looking at the final product of the solved Schrödinger equation. So what these quantum numbers are just ways to describe the characteristics of an electron. So this is our electronic structure of an atom, a more specific, detailed electronic structure than we've talked about previously. So these quantum numbers describe different characteristics of an electron. So I'll just, write those down. So we have our n quantum number, which we've talked about before. N should look familiar. That's our energy level or our principal quantum number. We have L, lowercase l, and then we have m subscript l. And so those are three of our quantum numbers. And then there's another quantum number we'll talk about later, m subscript s. So these quantum numbers, these first three, and we'll talk about this one later, ms later, they describe the energy, shape, and orientation of the orbital or the probability map of finding an electron. So that's what an orbital is. It's just a representation of where you will find an electron. So probability of finding an electron. Because remember, we can't know the location of an electron specifically because of the Heisenberg uncertainty principle. So we have to think about probability of finding an electron, and that's what these shapes of these orbitals come out to, probability of finding electron. All right, so let's go through all of these different quantum numbers. So the first one we've already talked about, the principal quantum number, or n. This identifies the shell energy level of that electron. So the shell determines the average distance away from the nucleus, and this is very much related to the other n energy level that we talked about with the Rydberg equations and the Bohr model. So Bohr did get this quantum number right, and these shells have integer values, any positive integer value, but not including 0. So n, our principal quantum number, can be 1, 2, 3, 4, 5, 6, 7, whatever, and so the shell, or the n principal quantum number, determines both the average distance from the nucleus and the energy of that electron. So as n increases, both distance from nucleus increases, but also energy of the electron increases as well. So again, you can kind of think of like rungs on a ladder. And as you increase your n value, you're going up your ladder. And so the higher off the ground you are, you're increasing your distance from the ground, but you're also increasing your overall energy. Okay, so let's look at the next quantum number. So our next quantum number is L, or sometimes I stylize it like cursive L just so you can see it better when I write it. And so this is our secondary quantum number. N is our principal. All right, so you can kind of think that is like the big overarching principal number. And so a subset of that is our L, our secondary quantum number. So this identifies the subshell. N identifies the shell. L is our subshell. So the subshell determines the shape of our orbital. Or you can just think of the probability map of finding an electron. And so L is equal to all of the integer values between 0 and n minus 1. Is that what I want to say? So L depends, the possible L values depends on what n value you have for that electron. So L is equal to all integers between 0 and n minus 1. So if, in this example, if n equals 4 for that electron, the possible L values, so I'll just say possible, the possible L values are all the integers between 0 and n minus 1. So L can equal 0, 1, 2, or 3. Again, only talking about integers. So notice here, because now we can include 0 with an L, but we can't include 0 with n, that there are 4 subshells within an n equals 4 energy level or principal quantum number. So in general, the number of subshells or L values possible in any n value equals n. So that means if we had, n equals 5, then L can equal 0, 1, 2, 3, 4. So you can see that there's 5 possible L or secondary quantum numbers within an n equals 5. All right, and so yeah, typically within a particular shell, the energy of those subshells increase with n. Typically, so that means an L equals 0 has lower energy than the energy of an L equals 1 or 2 or 3 or 4 within one particular shell. So subshells, remember, determine the shape of the orbital. So each one of these numbers, these subshell possibilities, has a unique shape to them. So what do these shapes mean? Those shapes have a letter designation. So these unique shapes that the subshells can have has specific letter designations to indicate their shape. And I'll show those shapes later. But just understand that each of these L subshell numbers that we can have has a letter designation, and each one of these letters has a unique shape. So when L equals 0, we call that an s orbital. If L equals 1, we call that a p orbital. 2, at L equals 2, that's a d orbital. All right, and so these are our letter designations. This is typically what we use, these letters, to indicate L, our secondary quantum number values. So typically how we write these, when we write orbitals, orbital shapes, we both want to indicate its principal quantum number, principal, and its secondary, when we want to describe the shape of an orbital, or where to find an electron. So typically what we do is write the principal quantum number at the beginning and then the shape of the orbital after it. So for example, if we have an electron that's in the third principal quantum number energy level and its L value equals 1, we remember 1, an L equals 1 is a p orbital shape, so we would write this as a 3p orbital or 3p subshell. Oh yeah, so that's what I have here. So the n number, our principal, is denoted at the beginning to indicate, okay, this is n equals 3, and then the p comes from our L secondary quantum number. That's our shape. So essentially what these numbers tell us, 3 tells us the size of the subshell or orbital, and p tells us the shape. So just in a number and a letter, we can determine its size and its shape. All right, and so just so you know, for an n equals 3, you can also, if n equals 3, then L can also equal 0, 1, or 2. 0 meaning S, L equals 1 equals P, L equals 2 is a d orbital. So that means within our n equals 3 energy level, we can have a 3s, 3p, and 3d subshell. So let's just practice naming subshells here, given these different quantum numbers. So if we have an electron that's in n equals 5 and L equals 2, so we know that the subshell will start with a 5, but let's remember those L quantum numbers. We have 0, 1, 2. So 0 is an S, 1, an L of 1 equals P, and an L of 2 is D. So if n equals 5 and L equals 2, then this is a 5D subshell. All right? And then let's, another problem. So why is there no such thing as a 2D subshell? Okay, so let's break that down. So 2D, that number 2 means that's its principal quantum number. So this is an n equals 2. So D tells us its shape. D is associated with its secondary quantum number. So L equals 2 if it's a D shape. So let's kind of work backwards here and see if this is even possible. So remember, if n equals 2, our possible L values are equal to 0 and all the integers all the way up to n equals 1. So that means our possible L values for n equals 2 principal quantum number is L equals 0 and 1, and that's it. So that means we can only have a possible S subshell or P subshell. So we don't have access to the D subshell. So this is why there is no such thing as a 2D subshell, and it's because of this definition of our secondary quantum number that the only possible ones are between 0 and our n equals 1. So there is a such thing as a 3D subshell because n equals 3, we do have a possibility of having L equals 2 to be a D subshell shape. Okay, so that's our second quantum number, our secondary. So now let's look at that last one, our magnetic quantum number, which is M subscript L. So typically I write it like this, so you can see like that this is an L and not just like some weird line. All right, so this last quantum number determines the orientation of the subshell. or of the orbital. Orientation of orbital. All right, so to get our ML values, you have to know both N and L, our principal quantum number and our subshell. So your ML values are equal to all of the integers between negative L and positive L. And so ML, the number of possible ML values, tells us how many orbitals are within a subshell. So subshell tells us the shape. Orbitals are how many different orientations you can have within that subshell. So for example, if L equals 0, then the only possible ML value can be 0. So let's just remember ML equals all of the integers between negative L, positive L. So if L equals 0, the only possible ML can also be 0, because negative 0, positive 0 is just 0. If L equals 1, that means we can have ML values between negative 1, 0, and positive 1, and etc. Well, let's just do another one. So if L equals 2, that means our possible ML values can be negative 2, negative 1, 0, positive 1, and positive 2. So all of these different ML values are different orientations. Different orientations of orbitals. And these orbitals make up the subshell, which is our L shape of orbital. All right, and so within the L equals 0 secondary quantum number, since there's only one ML value or magnetic quantum number available, that means that our L equals 0 shape, our S orbital, only has one orientation. So S, I'll say S subshell only has one orbital orientation, and you'll see why when we look at the shapes. Orbital orientation. But if we look at L equals 1, we can have 3 different orbital orientations. Or then I think here, for how many orbitals or orientations are there within a D subshell. So if we think of a D subshell, that letter designation is related to one of our L values. So when we have a D subshell, that's L equals 2. So that's, this example. And so if we count how many orbitals or ML values there are within L equals 2, there's 1, 2, 3, 4, 5. And so in general, what you see up here, there are 2 times whatever L integer you have plus 1. That's how many orbitals are within a subshell of L. So remember, subshell is L. Orbital are the numbers of ML magnetic quantum numbers that you have. So let's kind of do the same thing for an F subshell. So F subshell is a certain L value. So if we look back at our key here for L values, we typically only look at these first 3, but let's just do F anyway. So 0, 1, 2, 3. So an F subshell is equal to L equals 3. All right. So L equals 3. So if we wanted to write out all the possible magnetic quantum number values, it's plus or minus all the integers between minus L and plus L. So our possible magnetic quantum numbers are negative 3, negative 2, negative 1, 0, plus 1, plus 2, plus 3. So total, that is 1, 2, 3, 4, 5, 6, 7. So there are 7 orbitals within an F subshell, or L equals 3. And we can also calculate that using this, general equation here, that there are 7 orbitals. That is equal to 2 times our L value plus 1. So you see how that works. 2 times 3 plus 1 equals 7. So that works out. Right, so that's another way to calculate it. Okay. So let's do a problem here, kind of summarizing all of these quantum numbers. Well, let's just kind of quick summarize them. All right, so we have our principal quantum number N tells us the shell, or the energy level of our electron. This is the same N that we talked about with the Bohr model. So as N increases, distance from the nucleus and energy of your electron increases. And these are all integer values starting at 1. Next, our secondary quantum number. This identifies the subshell or the shape of your orbitals. So L are all the integers between 0 and n minus 1. So again, we have to identify what our energy level or n principal quantum number is before getting an L secondary quantum number value. All right, and then each of these L subshells has a shape which is designated by the different letters. So 0 is S, 1 is P, 2 is D. Those are the ones we mainly worry about. And then we have our magnetic quantum numbers. So these are the different orientations of these shaped orbitals. And so ML, or M subscript L, is equal to all of the integers between negative L and positive L. All right, so let's see which of these following sets of quantum numbers are not valid using, our definitions that we came up with. So let's look at this first one. So n equals 1. So let's just think, okay, if n equals 1, what are our possible L values? So L is 0 to n minus 1. So n minus 1 is 0. So our only possible L value that we can have is 0. And so what's listed here is 0, so that works out. Right, so if we have an L equals 0, what are our possible ML values? ML are all the integers between minus L to positive L. So the only possible ML value for a subshell of 0 or S is equal to 0. So this first one checks out. So this one's good. We can have an N equals 1, L equals 0, ML equals 0. So if we wanted to write the actual orbital for this, this would be so if L equals 0, this is an S orbital or subshell. So then this would be a 1s. This electron would be in the 1s orbital or subshell. Okay, so let's move on to the next one. So n equals 3. So I'm just going to go ahead and write the possible L values for an n equals 3. So if n equals 3, we can have 0, 1, or 2. And so what's listed here is n equals 2, so that checks out. Yay. So n equals 2, that works out. And then last, the ML values. So if L equals 2, our possible MLs for L equals 2 would be negative 2, negative 1, 0, positive 1, positive 2. And so what's given here, negative 1, so yes. So we can have an n equals 3, L equals 2, ML equals negative 1. So that checks out, right? And so if we want to write the subshell for this, we need to write our n value and the letter designation of L. So if L equals 2, so 0 is S, 1 is P, 2 is D. So this would be a 3D subshell. All right, last one. So n equals 3. So possible L values are 0, 1, and 2 again. So here we see L equals 3 within this answer. So this is not possible. So an L equals 3 is not possible within an n equals 3 principal quantum number because L can only equal all of the integers between 0 and n equals 1. So that last one is not possible. So the answer here is L equals 3 in an n equals 3 is not possible because L has to be less than n minus 1, or less than or equal to n minus 1. All right, so let's do another problem, checking out the different quantum numbers possible that we can have. So let's look at this problem. What are the possible values of all 3 quantum numbers for the n equals 4 shell? So all the possible quantum numbers within n equals 4. So we know it goes n, L, and then ML. So we're given n, that equals 4. So the possible L values are L equals 0, 1, 2, and 3. So those are our possible L values. Within those L values, there are certain ML values. So let's kind of take inventory of all of those. So if L equals 0, what are our possible ML values? So this is kind of my little table. So this is within an n equals 4. So if L equals 0, our possible MLs can only be 0, right? Because ML is only the integers between negative L and positive L. So let's just keep going through the list. So we did L equals 0. So if L equals 1, what are our possible ML values? We can have ML equals -1, 0, and +1. There are possible MLs within each of these L secondary quantum numbers. Oop, I'm running out of space. All right, so then let's do this again for our L equals 2. So if L equals 2 within our N equals 4 principal quantum number, then our possible MLs are -2, -1, 0, +1, +2. Okay, we're almost home stretch. All right, lastly, if L equals 3, because that's our last possible one, right? Yes, so we did 0, 1, 2. Now let's do 3. If L equals 3, our possible ML values are -3, -2, -1, 0, +1, +2, and +3. So there are all our possible values for quantum numbers within the n equals 4 shell. So how many total orbitals are these? So let's just count them up. The number of orbitals are each of the possible ML values within each subshell. So within the L equals 0, there's only one possible orbital there within L equals 0. Within L equals 1, there are 3 orbitals or 3 orientations. Within L equals 2, there are 5, and then L equals 3, there are 7. So all I'm doing is just counting up the individual ML possibilities that I put. And so if you add all of those up, you should get that there are 16 orbitals total within our n equals 4 energy level. All right, and so you note here, for any shell, with any n shell, so in this case it's n equals 4, there are n squared number of possible orbitals, and these are all of the possible MLs that we just calculated or determined right here. So in this case, for n equals 4, 4 squared is 16, and we got 16 orbitals. So if you did this same thing for n equals 5, all right, so you can do this at home or on your own. For an n equals 5 shell, you should predict that there are 25 orbitals total if you do this same analysis. So we would essentially have to do another line here for L equals 4. L equals 4, and do the same ML analysis and calculate and add up all of those total orbitals. All right? Okay. So those are all our quantum numbers. So I know I just introduced a bunch of just numbers. So now let's actually put those shapes into representation so you understand what they look like. Essentially, those letter designations of the shapes of the orbitals. So remember, when we talk about shape of orbitals, this is just the probability map of finding an electron. So with all of these shapes of atomic orbitals, we are looking at our L, our secondary quantum number values, because L determines shape of orbital. So our first atomic orbital that we will look at is our s orbital, or when L equals 1. So this is a completely spherical orbital that the probability of finding an electron just resides within a spherical shell around the nucleus of the atom. So essentially, an s orbital is just completely spherical, and so you have a high probability of finding an electron in this shape. And so that's when L equals 0. But remember, you can have L equals 0s within all of your different, n equals 1, 2, 3, 4, 5, right? So as n increases, the total volume or the size of your s orbital increases. And that's what you see here. So in these 3 representations, you have an L equals 0 because we're looking at the s orbital, right? But this is an n equals 1 s orbital. So you see it's the smallest. And then in the next one, you have n equals 2, n equals 3 because of the first number out front. It tells us its principal quantum number. And so you see the size of the s orbital increases. And so that makes sense because when we looked back at our principal quantum number up here, our definition, that number n determines the average distance of that shell away from the nucleus. So we said as n increases, the distance from the nucleus increases, and also the energy of the electron increases. But what you want to see here is that distance from the nucleus increases. So this is why the size of your s orbital changes as you increase your principal quantum number. All right. So yeah, as n increases, the size of that s orbital increases. Essentially, the size, that the probability, we have to increase the size of the orbital to make sure that we can find that electron within a 90% confidence. All right, and so essentially these orbitals, these s orbitals, as you increase your n value, they kind of nest within one another. It's like a Russian nesting dolls. All right, so our s equals 3 kind of encompasses, or sorry, 3s orbital encompasses our 2s and our 1s. And so these are certain distance from the nucleus where you'll find an electron located at these particular orbitals. All right, so let's talk about our next orbital shape. We just talked about the s orbital, which is when L equals 0. So now let's talk about the next one, which is L equals 1, or our p orbital. So S is a completely spherical shape. That there's no, you can rotate a sphere and it doesn't matter its orientation. So that's why there's only one ml value, because it doesn't matter how you rotate a sphere, it's always the same. But within our p orbitals, or L equals 1, it's a dumbbell shape. So these are directional. And so the three different orbitals, or ml values, within our p subshell, we can have different orientations. And these are our different ml values. For a L equals 1, ml can equal -1, 0, or +1. So each one of these ml values are a different orientation, and we label these with a subscript based upon the axes that they are centered on. So with these dumbbell shapes, one of them, so this is like our different ml values. This is when ml equals -1 is our p subscript x orbital. It's subscript x because the dumbbell lies on the x-axis. So our other ml value, 0. All these ml designations I made, they're just arbitrary because the real designation is the axes that they lie on. I just want to show that these 3 ml values, based upon L equals 1, corresponds to these different orientations. So our next orientation is PZ. So you can see that the dumbbell shape lies on the Z-axis. And then lastly, PY is where the dumbbell lies on the Y-axis. So that's like a nice question to ask on an exam, is I just show you like one of these shapes, and then you have to predict, okay, what orbital is that? So you would have to first identify, okay, that's a P orbital because it's a dumbbell shape and it lies on the Z-axis, so this is PZ. Okay, so that's our L equals 1, or p orbitals in those different orientations. So our last one that we'll concern ourselves with in this class is the L equals 2 subshell, which has our d orbitals, or d orbital shape. So d orbital shapes aren't a dumbbell, but they're kind of like a more complex dumbbell. A dumbbell has 2 lobes, so the d orbital has 4 lobes, except the weird dz squared orbital. So just know that as you kind of go increase your L value, the shapes get more complex. Like S is the simplest because it's just a sphere, and then P has 2 lobes, D has 4 lobes. All right, and so here are our 5 different d orbitals, because remember, when L equals 2, our possible mLs are -2, -1, 0, +1, and +2. So there's 5 orbitals total, and see, these are the 5 orbital shapes that come from L equals 2, or our d subshell. And so here are those shapes. And again, the letter designation that we give and the subscript depends on what the orientation is of the d orbital. And it depends on just the XYZ coordinates. This is all in 3D space. So if we look at this first d orbital, if you look and see where the 4 lobes lie, what plane it lies on, will give you the subscript designation. So this first one, you can see that the 4 orbitals lie, if you kind of go like one, this isn't a very good picture. Okay, it's kind of laying flat with the z-axis pointing up on it. So you see that those 4 lobes lie within the xy plane. So that first d orbital shape is our dxy orbital. So then if we look at our next one, the next shape here, I don't have these in order. I really should have them in order. Next, you can see that the lobes lie within the xz plane. All right, and then the y-axis is kind of like spearing through it. So this shape is our d, or this orbital is our dxz d orbital because that the lobes lie on the xz plane. Then what's this one? So I see there's a lobe there, there. So essentially the x-axis is spearing through it, and the lobes are lying between the yz plane. So this orbital is our dyz. All right. So you just kind of see where is that those lobes lying. And then here are the kind of weird ones. So here are the weird ones. So we still have 4 lobes in this picture, but the lobes are no longer lying between the xy axis, or sorry, between the different axes. So instead, this this shape is lying like on the x and y axis. That one lobe is like directly on the y axis, and the other one is directly on the x axis. So this specific d orbital is our dx squared minus y squared. So these two are easy to mix up. Just know that dxy, the lobes are between each of the, I guess, quadrants. But then in our dx squared minus y squared, the lobes actually lie on the axes themselves. So I'll write that. Lobes on axes, right? So they lie along the given axis. All right, so here's our last shape. It doesn't necessarily look like it has 4 lobes. It looks more like a dumbbell with a belt on it. But really what's the dead giveaway here for our orbital shape is that the whole lobes, they all lie on the z-axis. So this is what we call our dz squared orbital, because all of the lobes and its belt kind of lie along the z-axis. All right, so those are our 5 different d orbitals. So on a test setting, I could give you something like this shape right here and ask you, okay, what orbital designation is this? And you would have to know, okay, it's a d orbital because there's 4 lobes, and the lobes lie on the xz axes between them. And so this would be our dxz orbital. All right, and so we will only look at SP and D, our F orbital shapes. If you kind of think about the number of lobes as we are increasing, S has 0 lobes, P has 2 lobes, D has 4 lobes, so you can just imagine how many lobes F orbitals have. They have 8 lobes, and so they're much more complex, and we won't go into that. All right, so those are our orbital shapes. So I told you that we have one other property of electrons to talk about, and that is our ms value. This is related to spin. And so when we talk about spin, these are how many electrons can be in one single orbital. And so I'll talk about spin, electron spin, and the Pauli exclusion principle in the next lecture video.